good morning. So yeah, first, thanks to the people from the organization to give me the opportunity to present what we are doing in the lab. So yes, my name is Paul Renault, and I am PhD student in the Multimode quantum optics team from LKB. And today I will present you the experiment we are working on. We call this experiment the SPOPO. I will also give more detail about pump shaping and machine learning. So this is my outline. So first, I will introduce what I mean by multimode quantum optics. Then I will present the SPOPO experiment, and finally I will also present some results about the pump shaping. So first, the introduction. So to explain what is multimode quantum optics, so I'm going to define each word of this sentence. So first, multimode. If I want to speak about multimode, first I have to define what is a mode. So I think you all know the Maxwell equation. So I define a mode as the solution of this equation. So basically, I can write my field like this, and my mode is f. All the information about the mode is the function f, which is solution of the Maxwell equation. So we have several examples of family of mode. I would say that the most famous one is maybe the TM mode, where we have like for each mode we have a spatial distribution. And but we also have the pulse mode. Each mode have like a Hermite-Gaussian shape. And finally, like we also have the frequency comb mode. The same, we have like a comb with a Hermite-Gaussian shape. In our lab, what we use is the last family, the frequency comb mode. So why? So if there is several advantages for this kind of mode. So the first one. So if we look the Fourier transform of like a Gaussian frequency comb, what we will observe is that we get this strain pulse here, and this is actually quite easy to produce in the lab. In the industry, you have pulse laser with different pulse duration, different repetition rate you can choose, and so you just have to buy it. And there is also other advantage. So we want to use this tool to do quantum information. So we need optical nonlinearity and entanglement. About the nonlinearity, it depends of the power. So and if and with my trained pulse, all the power is concentrated into the pulse. And if I do like a easy calculation, what I know is that in the lab with the type of laser we have, the peak power is quite huge. It's like more than 10, it's around like 10 kilowatts. So it's quite easy to get nonlinearity in this kind of situation. The other advantage is like the entanglement. So we need, as I told you, we want to work on multimode. So if I take my spectrum here, so it's one mode, but inside my frequency comb, each case is actually a mode, is solution of the Maxwell equation. So what in the ideal case, what I could do is it will be to entangle each teeth of my frequency comb here. So now, so this was like the classical case. Now the quantum part. So in the quantum regime, I can write my field like this. So here, so you have like a sum, actually. So here you can see it like a sum of harmonic oscillator, where it's different, a little bit different from the classical regime, because here you have the annihilation operator, and, but you still have the function f, which is my mode. So basically, here, for each harmonic oscillator, the information about the state is in the annihilation operator, and the information about the mode is in the function f. So because you are in quantum regime, we have the Heisenberg relation, and the annihilation and creation operator are related with the operator Q and P. So this is a quadrature of the quadrature operator. So the equivalent in the classical regime is like the quadrature of the field, like the cos and sine part. But it's also like there is also an equivalent in the quantum mechanics, because it's like it's the position on the momentum operator. So an example of state we can define with this operator is just the vacuum state. So you have like nothing. So you are like center on the Fresnel space, and you have this uncertainty circle because of the Heisenberg relation. But we are in a lab, so what we want to do is to measure this kind of state. So in the lab, we use what we call a homodyne detection. So it's a projective measurement. So we have this state, phi, we want to measure, and it's interacting with a local oscillator here. And we shape this local oscillator with the mode f, which is the same than the mode of the state phi. After we are collecting the light with photodiode, and if we do the math, what we will see is that the current here is proportional to the fluctuation of the field, of my state. And so here also it depends of phi, which is the phase of my local oscillator, and which is the angle here. So during the measurement, when I'm scanning the phase of my local oscillator, I will do actually a tomography of my state. But this is vacuum state. It's not really interesting. In the lab, we produce a quantum state with what we call an OPO cavity. So it's basically a cavity, like a Fabry-Perot cavity. And we put inside the cavity is resonant in the red wavelength. And we put inside a nonlinear crystal. And we pump this cavity with blue light. So we will create one blue photon will create two red photons, an idler and a signal, and they are entangled between them. And we have in the degenerate case, so we have energy conservation, and in the degenerate case, the frequency are the same. So if we write our Hamiltonian, it's something of interaction, you have something like this, an annihilation of one blue photon for the creation of two red photons. And in the degenerate case, and if the pump power is high enough, we could do this. We can do this approximation, which is like the Hamiltonian of squeezing state. So how it looks in the Fresnel space is so it's different from it's a blue figure. It's different from the vacuum state, as you can see. So you have like you can see that your fluctuations are squeezed in one direction, and anti-squeezed in the orthogonal direction. So it means that if I plug my homodyne detection in one oscilloscope, what I will observe this screen. So the first one, the first screen is when I'm in the vacuum state case. So I do not pump my cavity. So what I observe is just noise. It's the shot noise. And when I pump the cavity, what I observe is that I will see some squeezing for some phase here on my noise is also anti-squeeze for other angle phi. But this is the monomode case. Now, as I told you, we are multimode. So here, so I still have my OPO cavity, but now in the multimode case, I'm pumping my cavity with a frequency comb now, a blue frequency comb. I mean output, I will have an output state in where my mode will also be a frequency comb in the red. But as I told, in the monomode case, we saw that the cavity has to be resonant in the red. So I have to make sure that my cavity is resonant for each teeth of my frequency comb. So to do so, we set the length of the cavity the same as our laser lens. So what happened if I took my two frequency comb? So one photon from a blue mode here can create two photons here. So they are entangled, but you have other choice. So from this one, we can create entanglement between the yellow one and the more green one, and etc. So what we observe is that we can create entanglement among this frequency comb. So this cavity is called the SPOPO. It's just like an OPO cavity in a frequency comb domain, and we have to make sure that the length is set to be resonant for this red frequency comb. So now I'm going to give you more detail about the experiment. So we have this our SPOPO, and as I told you, if we look into the frequency comb, what we have here is like a distribution of entangled photon pair, and they are on each teeth of my frequency comb. And if I want to write my Hamiltonian here, it's a little bit different than in the monomode case. So here I have like a sum for the mode M and N. This is the mode of my red photon. And here, so I have these two correlation operator. And L here is a matrix. We call it the joint spectral distribution, and it acts like a probability to create these two modes. So here it's like a calculation of this distribution with the setting of our experiment, and as depend of the wavelength of mode N and the wavelength of the mode M. So, as I told you before, we have entanglement, so it's good, but we want to check it on the experiment. So we have access. We need to do a measurement, and as I showed you in the introduction, with homodyne detection, and with this kind of homodyne detection, we will get access to the variance of the noise. So also what we need to do is to shape the mode we want to measure on the local oscillator. So here because we are in the frequency domain, we have to shape the structure of the spectrum of the local oscillator. So here, so that's why we use what we call a pulse shaper. So we just have like a SLM in the frequency domain. So a SLM is just like a screen with a pixel, and each pixel can modulate the amplitude on the phase of your beam. And because you use it in the frequency domain, you can modulate each part of your spectrum. So also I told you that we work with frequency comb, but here we are manifestly limited by the size of the pixel. So we play more with frequency bands and frequency comb, of course. And now what I want to check is that if I take two parts of my spectrum, I have to answer to the question, are them inseparable or entangled? And I can also check that one, for example. And I use, for the inseparability criterion, this formula. So I need to get access to these two variance terms. So first, I shape the local oscillator with the red part. So just one thing. So the red is like the part of my spectrum, and the blue is the other part of my spectrum. It's not the pump on output stage. Just so here, I first shape my spectrum with the red part, and I can measure this variance term. Then I shape with the other part. I measure the blue variance term, and after I take the sum and the difference to get access to this term, and I can calculate my separable criterion. So this is the result we have. So here I show you an example for just one bipartition, but we can do the same for all the bipartition of our spectrum, and it gives us this graph. So in abscisse, you have the number of the bipartition, and you have two dot curve. So one, the blue is for the inseparable criterion, and the red is for the hyperarc criterion. And we rescale the y scale to make that the threshold is 0. So it makes that if we are below 0, it's good. If we are above 0, we are not hyper or not inseparable. So what we can see is that for all the bipartition, the blue dots are always below 0, but so we are always inseparable for each bipartition. But for the EPR, it's not perfect. It's good only for the first 100 bipartition, but we still have entanglement. So this is the entanglement part. But in the introduction, I also speak about squeezing. And what I would like to see is the measurement of squeezing. So how can I do? So this is the Hamiltonian I've got. And if I can, as I told you, with the homodynamic detection, I can measure a covariance term. So here, in these two, I plot these two matrices, is the measurement. So in the frequency band basis of the covariance matrix for like for the Q quadrature and the PP quadrature. And so actually, for this Hamiltonian, we are also in the frequency band basis with M and N. So basically, if we diagonalize this Hamiltonian on this matrix, what we will get this Hamiltonian. So you can recognize a superposition of an Hamiltonian of squeeze state. And in the matrix, what we see here is that so we have a new basis where you have no correlation, and here we have some term in the diagonal. So it's like a coefficient of the noise, which means that here, so we have some coefficient above 1. It means that we are anti-squeeze, and below 1 we are squeezed. And what we can notice is that in this new basis, the pair mode if they are squeezed on one direction for Q, for example, they will be anti-squeeze in the orthogonal direction here in P. It's the case for the first mode, like the mode 0, for example. But what we need to know now is what is this basis where we have the diagonal? It's so just what we have to do is to take the eigenvector of the diagonalization, and it gives us this mode we call the super mode. And it's quite interesting because we can fit them with Hamid-Gaussian mode. So this is a scheme of the experiment. So we have like our source, the train pulse. And the light is divided in two paths. One path is to create the pump, to pump the cavity. And the other path is the local oscillator path. And we shape this beam to then do the Omdan detection. And this is in real life, so it's more complicated. And so we have our laser here. The Spopo cavity is actually in the plexi box here, and we have like here it's like the part of the red pulse shaper, and here there is a small box here. This is Omdan detection. But here, this is more detailed photo of the Spopo cavity. So as I told you, we have here it's different than in the scheme I showed you before. Just so it's because here we use a lot of mirror because we need that the cavity is quite huge. The length of the cavity is quite huge because, as I told you, the length of the cavity is the same than the laser. But our laser length is 4 meters. So here we need to find to set the distance with 4 meters. So, but I have still one limitation for my squeezing measurement. That now I need to shape this Hamid-Gaussian supermode. So, as we saw, is that the light is coming from the same source, the laser. So here, this is the spectrum of the laser, and this is the spectrum of my output state of the Spopo. So in blue it's mode 0, and in green the mode 6. And if I superpose the spectrum of my local oscillator, sorry, I have this. So as you can see, the envelope is not perfect with mode 6. So I'm quite limited to shape my local oscillator in this configuration. So what we use in the lab is a photonoc crystal fiber here. We put just before the pulse shaper. And this, we have like a nonlinear, we use the nonlinear effect of the PCF to make the spectrum broader in input of the pulse shaper. So here we start with a 10 nanometer spectrum, and in output of the fiber we have like this kind of spectrum. So now, with this kind of configuration, we can now measure the squeezing. So this is a squeezing curve for the first 4 mode. So we did the measurement with a spectrum analyzer, which means that it's different than an oscilloscope because it takes only not the noise, but the level of the noise. So it's the amplitude of the noise. That's why you have this kind of oscillation. And so the bottom corresponds to like the squeezing angle, and the maximum corresponds to the anti-squeezing. And what you observe is that so the squeezing is decreasing as dependent of the mode. And also we can also plot the covariance matrix in this basis. So the main terms are in the diagonal. We still have some correlation here, but I think it's just because it's because of the difficulty to shape higher order modes. So now I'm going to speak about pump shaping. So what I show you is that we have like superposition in output of the Spopo. We have superposition of squeeze state on multipartite entanglement, but there is no dynamic in our system. If we want to play with the output state, we have to change something. Sorry, in our system. So we have our Hamiltonian here. And so the only thing we can change is the Jones spectral distribution. And if we derive the Jones spectral distribution, you have this. So the first part depends of the phase matching of the crystal, and the other part depends of the pump. So first, we can't change anything inside the cavity. It's too hard to realign every day if we change the crystal. But the only thing we can change is something about the pump. So here, what we use actually is the same than with the local oscillator. We use a pulse shaper. So with the pulse shaper, we can modulate. We could modulate the amplitude on the phase of some frequency band of our pump pulse. But since we add some, we can add some relative phase between some part of our pump spectrum, we have to reconstruct fully our covariance matrix. So we use that's why we use a multi-pixel homodynamic detection. So to get access to the Q and P covariance term, but also to the QP term. So this is the first result. So here, this is a full covariance matrix for the usual spectrum of the pump. And if I add like a half pi on the half of the spectrum, I've got this covariance matrix. And as you can see, we actually add this correlation in the QP term. But one thing, one difficulty here is that what I want to do is to play with the output state of my cavity. And why I see this curve is quite, because after we do like a diagonalization and etc., it's quite hard to have an intuition about what will be my mode, my squeezing, if I change this part or this part of my blue spectrum. That's why we decide to use a machine learning algorithm. So we try two algorithms. So the first one is about reinforcement learning with projective measurements. So we have like one agent, and so we have to train the agent to have like to optimize our state. So this agent can do an action on our system. And here, the state is the calculation of our joint spectral distribution. So it's the state S, and after from this state, we calculate a cost function. And if the cost function is good or not, the agent will get a reward or not. And after, it will be it will have some consequence about the next action of the agent. So the action of the agent are randomly choose, but there is still like a probability distribution which depends of the state. The other algorithm is like just a neural network algorithm. So we have this here it's the input of our system, and here we calculate the cost function. So this algorithm was made by already written by a lab in Australia, and we just use it. And just the characteristics that it used like 4 hidden layers, and each layer has a 64 node. So so we can use these two algorithms. On the action they can we can do for the training is the modulation of the amplitude on the phase. So just for the neural network, we have like an interval, a continuous interval for the action, and for the projective simulation one, it's a discrete interval. And what we ask after the training, the algorithm is to say, okay, we want to optimize the squeezing on the first mode. So we ask him to optimize this function f here. And this is the result we got for both algorithms. So here, this is the two spectrum we have to send it to the pulse shaper. So it's quite good because they are quite similar. We took that one because we said, okay, it's more symmetric, so it should work better. And so we measure after we have implemented this blue spectrum on the Pearl shaper. We measure the full covariance matrix here, and after, so we can diagonalize it and get the supermode, and after measure the squeezing on the supermode. So we got this result. So here on this graph, in the axis you have the mode, the supermode, and you have two kind of dots. So the black one are the squeezing where we are not when we use the usual point beam, and the red is when we use the solution of the algorithm. And what we can see is that actually on the first mode, the squeezing is optimized. Here we run something like almost 1 dB of squeezing, so it's quite significant in the domain. Okay. So in conclusion, we show you that we can with the SPOPO cavity, we can measure like entanglement, multipartite entanglement on superposition of a squeeze state. And but the thing is that if you want to play a little bit more with this kind of state, we have to do to use machine learning. But it's just like the beginning. It's just one try. What I didn't say is that here with the result I show you is just when we use amplitude optimization. And what we could do is to use the phase optimization, and also to play with other target state, like if you want to optimize another mode, or if we, for example, we want to have like a flat squeezing, it means that the same values of the squeezing for each supermode. So this is the group. Okay. So Thibaut and Francesco have also taken part of this project. So Francesco is a theoretician, and he works especially on the machine learning thing. And Thibaut, he works on the experiments. So we take the measurement together. So we have Nicolas Tres, Valentin Parigi, Claude Fabre, and Mattia Falcher, the permanent. On the SPOPO experiments, we are like me, but also Kang, Ganel is somewhere here, and Alex, a former postdoc, and now the new postdoc, David. So thank you for your attention.